wait till 8:07, then we will start. Okay. So this is a live coding session, but I think in the previous session, did we discuss the intractability, NP-completeness, all those things? I think we could not discuss, right? I think Atul told me to discuss that before moving into the live coding.
Yeah, that was incomplete in the session.
Yeah. So I would at first discuss some of that, most of that. We will complete that topic and then we will go to live coding. Anyway, this week live coding is very lightweight. There are no difficult questions, just one implementation of KMPs. So, but this topic of interactability is something very nice, and it may not be required that much for every one of you, but it's certainly very nice to understand this topic. And those of you who are planning to go into academics, then it is the heart and soul of algorithms, advanced algorithms. So let's discuss this. So before moving into that topic, any comments till now, since we are kind of
week 10 practice assignment question 2.
Week 10 practice assignment question 2. Okay. Just a second.
I haven't gone through the explanation. I mean, didn't try to, just wanted to understand.
Practice assignment.
And subsequently 3 also.
Yeah, just a second. Okay, so week 10 practice assignment question 2, right? Do you want to implement? Yeah, so even if there is no collision, driving car, still you are traversing it in that manner. What will be the upper bound of running time complexity of searching a pattern plain text using the above implementation rabbit? Yeah. What is exactly your doubt? I mean, exact.
Now, how to approach this?
So, is the Rabin curve algorithm clear?
Yes, I've gone through that.
Yeah. So, I think see, Rabin curve algorithm, it goes like that, right? I mean, if you see it, even if there is no hashing, right? Even if, I mean, sorry, no collisions, then also it has to check those subparts, and it should go like that to check the pattern.
Yes, false positives it has to check.
Right. So in that case, in anyway, in whatever, even if there is no collision, then also it has to check all the things. So it's all possible patterns. So n is the length, and you are traveling. The pattern is of m length, so it is n, irrespective of the number of collision. Even if there is collision, then also it would travel that much. Sorry, no collision, then also it would travel that much only. So that's why it is n. Okay, the mainly the rolling hash functions comes into your Knuth-Morris pad KMK algorithm, and that's why it's advantageous. That's why you are gaining that complexity, reducing that complexity to linear time. Okay. So, so it's better that you go through Ravenclaw once more, and I think then it should be clear. I mean, it's kind of the main concept part of Ravenclaw. It's okay. I mean, irrespective of the collision, it should go through all the matchings, right? M length matching for all n length string. So all possibilities are n into. That's it. Subsequent questions. Subsequent question is on what or state the automata reaches, right? So you have to just traverse through it. Is there anything else coming, or the general approach you want to ask? Wait, I'm sharing. This question, right?
Yes.
Yeah. So here, just what you have to do is, what is the string given? A, B, B, A, B, 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 whatever. So just traverse through it. So let's say, what is the start state? 1, right? Okay. So you start from 1, assume that you got an A. So go to 2, like that. Then there is a B after A, right? So from 2, take B, go to 3, like that. You have to go, and once this whole string is finished, whichever state you reach, that is your state. That is the answer. What state the following automaton reach? Yeah. Okay, so this automata concept is actually why we call it automaton, but it is actually so it's more related to another subject of computer science, but doesn't matter. So that subject is theory of computation. Right. So before, uh, so this subject actually deals with this. This question is very simple. You have to just traverse through it. But the concept behind this is how things work. I mean, an algorithm works. This is the abstract definition of a machine. Now, what is a algorithm or what is a machine? In this sense, machine means algorithm. I'm talking, huh? Not the general definition of machine, but in terms of algorithm. So what is an algorithm? It should halt. The main difference between the main definition of algorithm is it should be some finite number of steps that runs on a given input, and
It
it
should
should halt.
terminate
It
somewhere.
should terminate, exactly. It should terminate. That I should be certain before starting the algorithm, I should be certain that it would terminate in near future. That's the identity of an algorithm. There are certain problems where we are not sure whether I mean, once I start running execution, once I start executing some program on that problem, there are certain kind of problem where I'm not sure whether it would even stop in future or not. It may go on till infinity, theoretically. On the system, if you run such a program, it would, after some time, it would show you stack overflow or buffer overflow or anything, any system resource used up, something like that. But in theoretically, it may run up to infinity. Problems like that exist, right? So those problems we call undecidable problems. I will come to that because this part is very important for coming into the NP-completeness part. So those problems whose solution we cannot decide that whether it would stop in the near future or not, it may run up to infinity, those problems are called undecidable problems. The other half of the spectrum is those problems whose solution may be slower, may be faster, I don't know, but what I can certainly say is they will stop in near future. That I know for sure. It may take some time, but it would stop. It, in no possible situation it would happen that the solution would run up to infinity. That is not possible. It should stop. All the set of these kind of solutions or these kind of problems, so to say, are, I mean, we refer to them as algorithms. The solution to this kind of problem is what we call algorithm. Okay, so here we are talking about algorithms in this course. So mainly this automata concept is asked by taking this string, you put this string and traverse through this, and whichever state you get to the last, that's your answer. But this automata word is more related to a subject called theory of computation, and in that we also learn about things like where it may not stop anywhere. I mean, it may run up to infinity, undecidable algorithms and all this. So from that's the background of this word, so to say. Only in terms of the question, I think it's you just have to travel and see where you are reaching at the end. So that was it. And this question
So
is
basically, it
huh,
is asking by traversing through this string,
yeah,
which node, particular node, one stops at.
yeah. Which node
Okay,
you are reaching once this stops. I mean, once this string exhausts.
okay, okay.
So take A, go over here, then take B, go over here, right? Then take another B. Now from 3, yeah, we got B to 4. So go to 4. After that again we got another A, right? The fourth one is A. So from
It will take
4,
to two.
yeah, yeah, after that it would get back to 2. So like this.
Okay.
Okay. So one important application, so it may seem trivial why this is asked, but you see that this particular type of question, it's really mapped to a lot of computer science application. Let me give you one example. So in software engineering, okay, three examples let me discuss. Interesting. So first is software engineering. You would, when you are planning a software, right? When you are there is a subject of software engineering also in the course. Maybe some of you would take that. And yeah, so when you plan a software, after that you would code down all those things, develop a module separately, integrate them, do unit testing, then integrate all of them. These things will be learned in software engineering. But basically, software engineering deals with how you should structure the program. It's like making the blueprint of a house, right? So in software engineering, there are specific kinds of diagrams where you show that what is the flow of the data from the user to the system, right? From this module to this module, then this module changes the data into another form, then from there it goes to another module. And now the first module also sends some partial data to the module that we are currently talking about. So basically, I mean there is a graph kind of structure, like this kind of structure. Okay, so from this state to this state it goes. Now, an input would only go from one state to another when there is a certain condition occurring. And if it is not occurring, then obviously the software would understand that there is some issue in the input. The previous state has not given me the correct result. On this result, I cannot work, right? On some module. So it would stop, it would halt the thing over there and maybe generate a log message. So all this planning, this kind of thing is actually represented at the end of the day like this kind of similar diagrams. So here you see 1, 2, 3, 4. Maybe that 4 indicate in case of software engineering some data flow diagram or other kinds of diagram. It may indicate you some modules of the software where it is working on a specific input and producing a specific output. Depending upon what output it produces, it goes to separate modules of the software. And you see the same thing is occurring over here. If 3 is occurring, sorry, 3 is producing B as the output, or basically it is taking B, then it is going to state 4. If it is taking A, it is going to state 1. So these are just the, this is very important, but very simple concept, but it's represented in multiple forms in computer science. Another very important application, and that is very real life application, is so we have our the router, right, in our home router. So whenever our router transmits a packet, I'm just making this thing very, I'm saying very crudely, not going into the specifics, just the overall concept. So when our router sends data, right? Packet means data. There is a specific sequence which is added in front of every data and at the end of every data set. That is, say let's say you send a message, that message on WhatsApp, or sorry, not on WhatsApp, maybe in email you write something, right? Now that email, the data corresponding to the email is the user data, which is important. Now all of that data is added with some bits in front of it and some bits after it. Okay. So those bits are prefixed. They are already decided that these would be the bits. Fine. Some kind, or let's say the scheme of what would be the those bits be, that is already decided. Now your router has a sequential circuit that would actually check that which part of it is the padded data and which part of it is the actual user data. Now that circuit is simply what? If you get one, let's say the padded bits are always 1101, suppose. Okay, 1101. So what you have to design in electronics, you have to design a circuit which would generate an alert when it sees 1101. One followed by another one, followed by a zero, followed by a one. Right? Only this sequence is a padded bit, and this should generate an alert in the router. Now, how can you generate, how can you design such electronic circuit? So you will simply design a sequential machine like this, right? Like here it is given that A, B, B, B. If you get this string, you go, which state do you go to, right? So in that case, I would just reverse the question. I'm reversing the question that I have already decided a state, which is the final state, right? And in terms of electronic circuit, assume that final state is generating the alert. Okay, and the question now says that what should be the circuit. Here the circuit is given, string is given, the state is asked. In my question I am stating the state is already fixed and the string is also given. Now I am asking you to make a circuit, I mean this kind of automata, right? This automata you have to draw such that when it gets 1101 it goes to a specific state. You have to design the automata. Now, once you design this kind of automata, arrow from one state it gets one, it goes to one state like that. Right? When you design the logic corresponding to this, this automata, right? Simply from this automata, simply from this structure, you can generate, you can make the electronic circuit. How can I say that? We have there is something called truth tables. Okay, so from those of you who are from electronic or CS or any this physics or kind of background, you know that. So we can generate the truth table directly from this diagram. Truth tables are tables which are used for, let's say, making electronic circuit, right? So directly from this diagram you can make a truth table. Now once you make a truth table, it's just as simple as connecting the circuit equipments. So simply drawing this diagram properly by understanding the logic helps you in making a circuit which can detect which part of the user data is the padded and which is not, and that helps. That is how your actual router works. Okay, so these things are very important, but in terms of our course, it's just this circuit stated course. That's it. Fine. So that was some kind of trivia about it. Now let's go to the NP-completeness part. Any question, any doubt in this, some trivia kind of discussion we had?
Sir, can you mention the important weeks for or the important concepts which may be asked for the OPP programming exam?
OPP programming important weeks. What do you feel are the important weeks? Let me ask you this question.
I don't know, sir. You should.
I don't know. Okay. Every student knows which are the important things. We just ask so as to get, I mean, to get confirmed. Whenever we study a subject, we know which these things are important. Now, see, anyways, so practice the. So first of all, one thing that I would say, practice the graph questions very nicely. So that is one thing. Other than that, everything is kind of similar, kind of basic normal distribution. Nothing much. It's very, I mean, the distribution is not normal, sorry, uniform distribution. But practice the graph questions properly.
Okay, sir. Thank you.
Yeah. Fine. So now let's go to this NP-completeness. So I would try to discuss this in the form of a story. So just a precursor to this NP-completeness, intractability, and all those things, they are more about analyzing an algorithm rather than, let's say, discussing or understanding an algorithm. So these are about situations on how to analyze an algorithm, how to say that this problem is very easy to solve or very difficult to solve, right? So, for example, I tell you a real life problem, right? I tell you a real life problem, and you have to think about how to solve this problem, right? Like the traveling salesman problem. If someone of you have already heard about it. So what is traveling salesman problem? Traveling salesman problem is, suppose these are houses and I am representing them as a graph, right? So suppose these are houses and arbitrarily they are connected. This is just a graph. Fine. Let's say like this, something like this. Fine. So these are houses. All these vertices are houses, and let's say this particular vertex is the start. Okay. Now I ask you, this is a salesman. The start means this is where a salesman is, and this salesman has to travel through all the vertices. It has to reach to all these houses, let's say. Okay. And it should do that in a shortest distance possible, as well as it should not repeat any house more than once. That is, it should not visit the houses more than once. Fine. So two main difficult things: do it in a shortest distance for shortest manner possible, while maintaining that you should not visit houses more than once. So this is what is the basic understanding of a real life problem, which we call traveling salesman problem. Now I tell you, this is the problem. You have to think about an algorithm to do it. If you simply think that okay, it's shortest distance, apply Dijkstra. No, Dijkstra wouldn't, right? Because this vertex visiting condition is not there in Dijkstra. So you have to think about some other approach. So anyways, so we would not discuss that thing, but the issue is this problem seems that it does not have any proper solution. If not proper solution is there. I mean, any efficient solution to solve this problem. There are no efficient solution to solve this problem, and that's why we call this problem as one of the NP hard problem. Now, what is NP hard? We will come to that after some time. But basically, the motive of this topic of NP completeness, reduction, intractability, these things, the main topic, the main idea is when you, as a computer science guy, see a real life problem, right? How to understand whether this problem is even solvable efficiently or not? That's the question, right? In terms of big problems which are solved in industries, right? When you see a real life problem, the engineers has to understand that okay, is it even possible to solve it? If it is solved means, I'm talking about solving means solving in efficiently. Solving efficiently. What do I mean by solving efficiently? Solving efficiently means solving in polynomial time. Solving efficiently means efficiently means polynomial time solving. Okay. What is mean by, what do you mean by polynomial time? Polynomial time means your input size, which is n. Let's say we represented it using n, right? N to the power some polynomial. Okay, sorry, not n to the power polynomial. N to the power some constant value. Now this constant can be very large. K can be very large, but that's not our concern. So K can be 1 crore, 2 crore, whatever. Still, we would say it's a polynomial time complexity algorithm. Why? Because if n becomes very large, then I mean, so let's say K is very, very large, right? But what I can always say is, if this is the case, n, whenever n is becoming very large than K, because n is input size, it may increase up to, I mean, it may increase a lot, right? So when n is very, very larger than K, then overall this function actually is quite efficient compared to other function where it's exponential, or let's say 2 to the power n, or let's say n to the power n, right? Anything. So that's the idea. So whether it is solvable in polynomial time or efficiently is the question that we are asking, and that this topic actually answers that question. Fine. And so now what we did is, we basically found solution to some problems which we said and which we analyzed to be in polynomial time solvable, right? So let's say Dijkstra, it takes n log n, I mean e log v time. Let's say BFS, it takes e plus v, I mean the number of edges plus the number of vertices. In worst case, it can take accordingly for complete graph and all, but basically BFS would take e plus v time, Dijkstra would take your e log v time, right? Like this for any most of the algorithms that we discussed took some form of the complexity which is either polynomial or logarithm or something like that. But some algorithms where there are multiple possibilities, like let's say like the one like traveling salesman problem that I discussed, even for let's say for some of the problems which we discussed in dynamic programming, right? So if you would not have used dynamic programming for solving subsequence, longer subsequence problem, right? What is happening in longer subsequence using dynamic programming? You are just storing the data which is already once computed, and that's why you are not doing the computation multiple number of times. But if I ask you, you do not store the data, rather you just compute it whenever it's occurring, like a normal algorithm, right? So how many possibilities were there? We discussed that, right? The tree can be growing, it can have multiple branches, the recursive, sorry, the I mean the complexity tree. So it is actually exponential time. So longest common subsequence is also an exponential time algorithm if you are not storing the data which you have already computed by using dynamic programming. So all these problems which takes a huge uh, I mean, huge number of possibilities, and huge, by huge I mean 2 to the power n, or x to the, sorry, n to the power n, that is exponential. Exponential. Okay, exponential means what? Power is n. Whatever we did, this base can be constant or the variable itself, the input size itself, but the power is some function of x, n, I mean. Okay, so it can be, so let's say f of n and g of n, right, where f of n is allowed to be constant, f of n can be constant. So other way to say this is the power of n can be 0 in f of n, right? But in g of n, power of n, let's say n to the power p is not equal to greater than 0. So that's what the basic idea is. The power should be some function of n. Okay, and it should not be reducible. So if you write some n log n and then you convert it into some polynomial form, that's not a uh, exponential function. It should not be solvable or reducible to a simpler form. So those algorithms where it takes an exponential time or exponential number of possibilities, and that's why you have to traverse through all those possibilities and check which is the answer, right? And those algorithms are exponential algorithms, and the other name given to these algorithms are intractable. That's it. That's the only idea. Intractable means exponential, that is, which are not solvable in polynomial time. Okay. And other algorithms are which we like Dijkstra's, those are solvable in some polynomial complexity. Fine. So that was the main difference between these two things. Now let's delve a bit deeper. So I told you that we have, let's say, problems, and from here we can have undecidable problems, that is, which are not decided, that means which are not algorithms, and also we can have decidable problem which are algorithms. Okay, and within this we have two categories which are fast or polynomial time, and the other one is slow. But what is the idea? The idea is they would stop. Okay, these would not stop, but decidable would stop. It may take more time in case of slow, in case of fast it would be taking less time. So slow means non-polynomial time or intractable. Fine. So this is the classification. Now the thing is, so general idea, these are p polynomial time, so this is the p class and this is the np class. So that's why polynomial time, non-deterministic polynomial time, NP. But let me ask this question, and if someone wants, please go ahead.
Polynomial time means it is solvable in finite time.
Infinite time. Finite time means both of these would stop. Both of these would stop infinite time. Sorry, both of them would stop infinite time. Infinite time. I mean, both your intractable and this polynomial time, that is NP and P. right? It would stop in finite time, That is, it would stop, but undecidable do not stop. So that's why I have written not algo. Undecidable are not algo. Decidables are algorithms. Now, only question is, it may be fast, it may be slow. In case of slow, it is NP or exponential or intractable. In case of fast, it is polynomial time. Both of them would stop, right? Both of them would stop. This and this, both of them would stop. But this may not stop. Undecidable algorithms may not, sorry, undecidable problems may not stop. So one example is there are multiple examples, or let's say the most famous example is the halting problem. It's not in the course of our discussion, but it's halting problem of Turing machines. So it may or may not stop. Fine. So only thing is algorithm should stop, and both NP and P are algorithms, right? Both of them are algorithms. So both of them would stop, but this is, let's say, 2 to the power n, this is, let's say, n cube. So it would stop faster, but it would take more time. But they would stop at some time, that is for sure. Now, one question is, if this is our graph, if this is our, sorry, not graph, diagram. So can I say this statement, and please hear this, this is very important for your exams and also for the general understanding. One more important point for this part of the chapter, I mean the intractability and NP-completeness, please read the lines very carefully. One line which is said in one way, if you just reverse it, the meaning may not be same. Okay, so read the statement very carefully, ask the doubts. Okay, so one statement I am making now, this is the understanding that we have now, right? This is what we have discussed. Based on this understanding, can I say that all NP problems are intractable problems? That is, they are not solvable in polynomial time. NP problems, this is the statement I'm making. NP problems are not solvable in polynomial time. Now, see, the idea is, yeah.
So this may not be true all the time.
Correct. Correct. So it may seem
No,
that,
I told because in the lecture, sir said that P is a subset of NP.
okay, so you have to understand why it is so. Na? So, okay, so any other idea you want to, other than that statement? That is something, that is the conclusion. But what led to that conclusion is what we are trying to discuss. Okay, so see, NP problems are not solvable in polynomial time. Now we have drawn this diagram that there are two branches, one is slow, another is fast. These are polynomial time solvable, and this is what we call NP, right? But if I am segregating these two, then this statement is very implicit, right? I mean, it seems it's very implicit. And non-NP problems are not solvable in polynomial time. That is the main reason we are segregating these two separately, right? But that is not the case. See, the idea is NP problems definition means what? NP problem does not mean, and this is the most frequently done mistake by all of us, that P means problems solvable in polynomial time. Done. NP means problem solvable in non-polynomial time. Wrong. NP's only accepted definition is problems which can be verified in polynomial time. NP means problems verifiable in polynomial time. Polynomial time.
That means the checking function.
Checking function, exactly. Okay. Never do this mistake of telling that NP problems are solvable in or are not solvable in polynomial time or are solvable in non-deterministic polynomial time. Why? The thing is, it's yet not proved. This thing that I wrote over here, that P is n cube and NP is 2 to the power n, that is correct. But this is not a statement. This is what we have observed till now. I can say NP problems, most of the NP problems takes exponential time to be solved. or I cannot even say that, because when I say most, then I mean that some may take linear time, I mean polynomial time. So basically that's the problem. See, NP's only accepted definition is this. You cannot rephrase or change the definition in any possible way, because that is wrong. Why that is wrong? Because we don't know whether this case, this that all NP problems would take some form of exponential time. This is not a fact. This is an observation till date. It's not proved mathematically.
No, then what will be the definition of NP problem?
This, that problems verifiable in polynomial time. I am not telling anything about problems which are solvable. Verifiable means what? Or checking means what? That you know that sir has discussed that this is the problem, it is given to you. This is I am telling you this is the solution to that problem. I am also giving you the solution. All that you have to do is check whether that solution is correct or not. That is very easy, right? I mean, when you have the problem and when you have a candidate solution, you can just check the semantics of the problem and check the solution. If it matches, then it is a solution. That's it. Like the prime factorization example that sir said, that you have been given a number x, and you have to factorize this number into two factors, let's say a and b, such that these two numbers are prime numbers. Okay, that is the question. Now this is a very difficult task to do, but if I tell you that these two numbers are prime numbers, and these two I mean these two are my answers to the question, right? So getting from x to these two is difficult, but get from moving from a b to x is very easy. I tell you that okay, a and b is my answer. What you would do is simply multiply and check whether the answer is x or not. And second thing that you would do is whether a and b are prime or not. That's it. So that takes order of, I mean, that takes a polynomial time work. But if I only give you x and tell you that you have to factorize x such that the both of them are prime numbers, there are multiple possibilities that you have to think about and then then get to the answer. Okay, so this is the concept of,
No, but if x is the product of two prime numbers,
yeah.
then x can only have these two factors, no?
Sorry, I said prime, right? So it should be co-prime actually. You can get to be co-prime,
Oh, okay.
not prime. So yeah, I mean, A and B should be co-prime that way. Okay, I mean both of them should not have common. So basically that's the idea.
So if a problem is a NP problem,
Yeah,
then and all P is a subset of NP.
don't think of P as a subset of NP right now. Huh? Let's move slowly. Just ask up to this whatever doubt is.
Okay.
Okay.
No, so if suppose we have NP problem, then we cannot be sure whether it can be solved or not solved in polynomial time.
Exactly, and that's why I cannot
It
say.
can be solved in polynomial time. It cannot be solved in polynomial time. We do not know.
We do not know as of now. We do not know. Okay, mostly the problems which we have seen, that we have yet not come up with a solution which is polynomial time, and that's why we kind of say that okay, all these problem takes exponential time, and that's why I put them into a bag. Let's call that bag of problem as NP, and I will only say that generally they take exponential time. I have yet not come up with even a single solution for even a single problem lying inside that bag which is polynomial time. But at the same time, I cannot even say that none of the problem would ever be solvable in polynomial time, because in that case I have to prove it, that there is never a possibility of solving each one of these problems in future in polynomial time. I have to prove that mathematically. That proof has yet not been done. If that proof would have been done, then we can say that NP is not equal to P, and P is a strictly subset of NP. Okay, P is a strict subset of NP. If that would have been provable, that some problems of NP are such that they would never be solvable in polynomial time. Okay, so in that case I can say that. But even that P is a subset of NP, it is correct from this standpoint that NP problems are verifiable in polynomial time. Why? Because I am saying if this is the accepted definition of NP, only think that this is the only accepted definition of NP. That once I give you the problem and I give you a solution, you can verify it in polynomial time. Okay. Now that is implicitly applicable to P problems because P is solvable in polynomial time. So obviously you can verify in polynomial time, right? So it's already solvable in polynomial time. So its verification would take lesser time, and that's why it is also polynomial time. So if I say the definition of NP is problem verifiable in polynomial time, then obviously P also comes into this definition, and that's why we call P is a subset of NP. That is the concept. Okay, but this is my question.
But we can never say P equal to NP.
Never. I mean, if you can say, you will get $1 million. I mean, if you can prove it. So
yeah, sir discussed about that open problem.
Yes. So that's the problem. So even if you write this statement, sorry, P is a subset of equal. P is a subset of say NP. Even some of the people would argue with you this is also not correct, right? And this is actually may not be correct, because when I say subset, I can assure you that this is never equal, right? When I say strict subset,
proper subset is never equal.
Yeah. So if I say that, it essentially means P is not equal to NP, right? It's or I can just write or from here. If it is a proper subset, it should never be equal. If it's not equal, I can say something like this: P is not equal to NP. If I say P is not equal to NP, that is solving the problem. That is, I mean, you are telling that there is. I mean, I can never come up with a solution of one of the problems lying over here, which would be solvable in polynomial time. That's basically saying this means saying this.
So is it safe to say that P can never be equal to NP?
No, you cannot say that, because once you say that, that means you are telling that in future we would never be able to come up with a polynomial time solution for any problem over here, which is over here. We cannot say P is a subset of NP very rigorously. We cannot say P is equal to NP. We cannot say P is equal to NP. Only thing that we can say is, as of now, our understanding is P is a subset of NP, but that is not a fact, or that is not a statement. That is just limited to an observation, and that's it. Nothing can be said about it, because once you say it, so let's say you say the same thing I discussed, right? You say P is a subset of NP. Why?
So if you say it, then it becomes a fact, but which is not true. It's still till dates is just an observation.
Yeah. Because it will have corollary. When I say P is a subset of NP, it has corollary this one. Once it has corollary this one, this essentially means the thing that I stated, that there you can in future you cannot come up with a polynomial time solution of any problem which is over here, lying over here, anywhere over here, right? So yeah, you cannot make that statement. Why then we say that P is a subset of NP, or why for normal purpose of discussion it is said, and sir has also discussed that. That is only because the definition of NP is problems verifiable in polynomial time, correct? If a problem is solvable in polynomial time, which is P, then it is also verifiable in polynomial time for sure, correct? So by that definition, I can say that P is a subset of NP, but it's not a fact. It's again an observation. Okay, so that is the idea why subset thing comes. So this is more important from your exam point of view. So please ask your doubt over here, that whether this definition and why P is a subset of NP, basically it is said. Is that part clear? Okay. Okay, so P, this is the definition of NP, and on the basis of that, we are telling that P is also verifiable in polynomial time, and that's why P lies inside NP. But I can never guarantee you whether P would ever go out and cover this whole thing, or P is strictly bounded over here. It can never go out. It's strictly bounded over here. I cannot say either of these two. Okay. Now, So that was regarding NP, P, the definition, what statements I can make, what statements I cannot make. Now, two other important things, since we are on this P and NP concept, we would discuss, and then we would go to reduction. Reduction is addressed first in the lecture. I would go to that after this. So the second concept that we would discuss today, that is NP complete and NP hard. Simply we would state it, not go into the details of it. So let's say these are all the problems that we have now, right? This is a set of all problems we have now in NP. Okay. Now the thing is, if you as a researcher, or maybe researcher in academics as well as in industry also, if you are working as a researcher and you have been given a real life problem and you have to give a solution, most optimum solution to that real life problem, right? So you would actually try to do some, think about some algorithm, maybe map that problem into some other form and then try to solve it, maybe convert it into a graph and then try to solve it, or whatever it is you do. But before doing that, what you try to do at first is whether this problem is even solvable or not in a efficient manner, or that is in a polynomial time. This is what I started today's discussion with. So this is what is done. So what you do, you as a researcher, what you generally try to do is you try to actually come up with one of the problem from the already given family of NP problems, right? Which is which is harder than all the problems in NP. Which is harder means which is difficult to solve. I mean, so let's say there are multiple problems in NP, right? Multiple problems are there. I want to come up with such a problem. I want to come up with such a problem, which from over here only, let's say I come up with such a problem, which is harder than solving any one of these problems. So let's say this takes 2 to the power n time, this problem. This takes, let's say, 3 to the power n time, right? I would say that all this problem, let's say, takes some k to the power n time. So this problem would take n to the power n time.
Sorry to interrupt.
Yeah.
Could you please briefly again tell about NP complete?
Yeah. I have not yet told about NP complete. What I'm saying is, just let's say I have a family of NP problems, right? This is just all the NP problems set I have drawn over here. Okay. Now I want to come up with a problem, another problem, or maybe one of these problems. Basically, I want to come up with one problem, let's say, and that problem is as hard as, if not more, it is as hard as solving the most difficult problem over here. That is basically I am picking up one of the problems over from here, which is the hardest one, or let's say, yeah, which is the hardest. Okay, so let me delete this circle, it's misnomer. So I'm picking one problem from the whole family of NP problems, which is the hardest one to solve. Now, why I am doing that? Why I am doing that? The reason is, when I would again go back to that story, that when you see a real life problem and you have to devise a solution to that, you at first try to check whether that problem is solvable in polynomial time or not. How to check that is, basically what you do is, you actually take one of this hardest problem, sorry, you take one problem which is over here, the hardest problem, and compare this problem with the problem that you are trying to solve. Now what do I mean by compare? Compare means reduction. I would come to that later, right? Compare means basically you are trying to convert one problem from another. In this respect, compare means that. Now which problem to which one, I would come to that again later. Basic idea is, if you want to solve a real life problem, then you have to come, in order to tell that this is very hard to solve, you must compare with all of this problem, right? But in order to avoid this situation of comparing that problem with all of this problem, we come up with one candidate, and that candidate must be the hardest one to solve, right? Then all of this problem, and you just simply compare your problem with this one problem. You do not have to do it for all the problems in NP, because you already know that this problem is the hardest one, and my problem which I am trying to solve, if I just compare the difficulty between these two, then only I can say that since this is the hardest one to solve among all NP problems, and my problem is more difficult than the hardest one, suppose you can make this statement by doing the comparison. Okay, suppose you can make this statement that my problem is harder than solving this hardest problem yet known, then I can say that this is an NP problem, sure, right? And I can directly say my organization that this is an NP, if it is industry, this is an NP problem and it would not be possible to solve it in a polynomial time. You have to relax some constraints in the problem and then I can try to solve it in a polynomial time. Okay, so that's the first thing. Otherwise, you would waste a lot of time on thinking how to solve this problem. At the end of the day, you would not come up with any solution after, let's say, it took you 2 years to try to solve it, and your research is going into vain. You are not being able to produce any proper result because it's implicitly not solvable in polynomial time. That's why this check whether even if it is solvable in whether it is possible to solve it in polynomial time or not, it is checked by doing this mechanism. You take one problem, the problem which you are trying to solve, compare it with the hardest problem available in the NP class, right? And if you can make the statement by doing the comparison that my problem is as hard as the hardest problem or more harder than the hardest problem, then you can directly say that okay, there is an NP problem, no doubt about it, and I cannot solve it in polynomial. So you have to relax the constraint, modify the problem somehow such that now I can try some other approach to solve it, right? Reduce the constraints. Otherwise, so the main concept is of NP complete. Before coming to NP complete, this is what I am discussing about NP hard. NP complete is just one more condition added with NP hard, nothing there. Okay, so the main concept of hardest, right? I have written hardest. Hardest is you have to save your time. You should not compare with all the NP problems which you have, right? All the problems which you have over here. You need not compare your problem with all of them. You just take the most difficult one, compare your problem with the most difficult one. If your problem is harder than the most difficult one, implicitly it is harder than all these problems, right?
So basically, benchmarking it with already all the known NP problems which have been solved already previously,
Correct.
which we have a knowledge of or database of,
Yeah.
and then basis the hardest amongst them all, comparing that, and then taking a decision.
Exactly.
So
That's how.
this total NP problems which we are having is already solved in the past by various other people.
As of now, in exponential time, not polynomial time. So traveling salesman problem also TSP, right? Traveling salesman problem also lies over here, but it is solved but in exponential time. See, one idea is why something is solvable. Every problem which has termination, right? That is algorithm. It would be solvable in polynomial time. It would be solvable in exponential time. Why? Because you can apply brute force. That's it. Apply brute force. All possibilities you check. So I ask you. So let's say I give you a particular string of, let's say, n length, and ask you about a specific property which is there in a particular permutation of that string. So you can apply some algorithm depending upon what property I ask in order to get to that permutation, and that may take some order of some polynomial time, right? Not order of, let's say that may take some polynomial time because you are using a efficient algorithm to reach to that permutation. But what is the other alternative? The not so brainy alternative. You are not using any algorithm or anything. Simply enumerate all the possible permutation, check one by one whether the property is applicable or not. Simple approach, n factorial, right? So this is taking you a polynomial time, let's say order of n to the power 4 time, suppose. Okay, but even without using your any algorithm or any brainy approach, you can just enumerate all the possible cases and check the property in each string. So that gives you n length string means n factorial permutations would be there, and this is actually similar to n to the power n. Oh, how I did this similarity, it's not important. This is, you can check it out. It's called Stirling approximation. But basically, n factorial means n to the power n. Okay, so this is exponential, super exponential. It's n to the power n. Input to the power input, not even constant to the power input. So basically, this is the idea. Any problem is solvable in brute force manner. Whatever problem I give you, you enumerate all the possibilities, check whether the conditions are satisfied in each one of them or not. So that's why most problems are actually this solvable. Their algorithms are already found and they are solvable. Sorry, they are not algorithms. Their solutions are already found because we do not have to find them. Algorithms come into the play when you think of some approach to solve the problem so that it reduces the time. But simply trying trial and error is not an algorithm. Right. So I think it's somewhat wrong to say those problems which have already been solved. It's, I mean, the idea is correct in terms of NP and comparison, whatever you said. But what I'm saying is, I think it is not correct to say that those problems whose approach is already found by someone. It's nothing to find about it. I mean, you are simply using trial and error. Finding comes into action when you find a way to do it in a non-exponential time way, where you are not applying brute force, where you are not applying trial and error, where you are not going through all the possible answers and rather making some intelligent guesses at each step to eliminate some answers and check only some specific solutions, which may be the probable answer for your case. Right. So that's what I want to say. Okay, but the idea is correct. We are picking one hardest one and then checking, I mean, my problem with it. Now, this comparison, this magical comparison thing that we discussed. Okay, so I did not give you the definition. So this hardest problem is called NP-hard problem. Okay. This hardest problem, which we are picking up as the representative of the whole family of NP problem, that it is the hardest one to solve. This is what we call the NP-hard problem. So all those problems which are as hard as all other problems in NP, those problems we call NP-hard problems. Okay. Now, what is NP-complete? NP-complete is NP-hard plus NP. Now, what is NP? NP's definition is only one thing, which is verifiable in polynomial time. Right? NP-hard means problem which are harder than any other problem in NP. Correct? So when I say NP plus NP plus NPH, what does that mean? The statement could be any problem which is harder than all other problems in NP. This statement is borrowed from NP-hard property, and that problem is itself a member of NP. Okay, so if I draw the graph, then it would be much clearer. Let me draw, sorry, not graph, the Venn diagram. So what I mean is, you can, okay, again I'm stating this is an observational idea, it's not a fact. Whatever diagram we have been drawing, whatever statements we have been making, these are all observations till now. Only statement is NP-hard problems, NP problems are verifiable in polynomial time, P problems are solvable in polynomial time. Other than this, none of them are statements, all of them are observations. So this, yeah.
No, but NP-hard and NP are two different things.
NP-hard and
NP, both are same thing, no?
No. So let's say I have one problem over here, problem number 1, right? And I have here another problem number 2. Now problem number 1 is easier to solve than problem number 2, but both of them take exponential time. Okay, so one takes 2 to the power n, another takes n to the power n. Both of them takes exponential time, but problem number 2 is more difficult to solve. Suppose. Okay, so I can say that problem number 2 is more difficult to solve. That means there exists at least one problem. There exists at least one problem which is harder than solving 1. Right? If I tell you that 2 is harder than solving 1, I can also tell that there exists at least one problem which is harder than solving 1. If that is the case, I can assure you 1 can never be the hardest. One can never be hardest, right? Never be hardest. Now, if one is never
Yes,
hardest,
because 2 is harder than 1, so 1 cannot be hardest.
correct. What is the definition of NP hard? It is hardest of all, right? NP hard's definition is it should be harder than all other problems. So if one is less harder than 2, right? So one can never be NP hard. NP hard, I mean. But one is NP. Why? Because it
So
is taking exponential time.
basically, NP, I mean, both are NP problems, but NPH is the hardest of all.
Exactly. And there can be multiple such NP hard problem. It may not be, because let's say two problem who is equally harder, right? And both of them are hardest, like the multiple maximum in a list, something like that. So like that. You have two, let's say 1, 2, 3, 4, 5, 6, 7, 7. So 7, 7, both of them are equally harder and both of them are max. So those kind of problems exist, which are equally harder and they are hardest of all others. Fine. So there is a huge difference between NP and NP hard. NP means any exponential problem, as of now by observation. Okay. NP hard means all problems which, sorry, problems which are hardest of all other problems. Fine. So that's why NP and NP hard are different. Now let me draw the diagram now. Okay. Now this is the definition of NP complete. NP hard plus NP. NP means verifiable in polynomial time, and NP hard means hardest of all other NP problems. So any problem which is harder than all other problems in NP, and that problem is itself a member of NP. Okay, now once I draw the diagram, it will be clear. And that problem is itself a member of NP, then we call such a problem as NP complete problem. So if I draw it, it would be something like this. This area is your NP complete problems, and this area is your NP hard. This whole circle, NP hard. This whole circle is NP hard. Okay. This whole circle is NP hard. Only the intersection part is, along with NP hard, it is also NP complete, because NP complete requires a problem to be NP hard first. And also it is a member of NP itself, right? So what do I mean by this? Let's take different regions of this diagram and let's make the statements now, or maybe the observations now. Let's take a problem which is lying over here, right? What does this problem mean? This problem means it is harder than all problems over here. All the problems in this area plus in this area, this whole both of this circle, right? It is
When we are drawing two circles, one for NP and one for NPH.
okay.
And NPC is the intersection of both of them. So it looks like NP hard has problems which are not even NP.
Which are not even NP is a wrong statement. Which are not NP. I'm not saying that it's coming in polynomial time. I'm saying it is also exponential, right? That's the dilemma. See, can you tell that NP means always exponential time? I cannot make it as a statement, correct? So if I cannot make it as a statement, I have no bound.
That is an observation till date, you said.
Correct. If I cannot make it as a statement, I cannot bound you to say that all NP hard problems should be a part of NP. What I mean is, and let's understand it in this way, that I can have problems over here which are taking exponential time, which are not, so that's why not even NP, even when you use the word even, that means you are assuming it is easier than NP. That is the wrong understanding. Okay, it is not in NP, but it is not easier. It is actually harder than all problems in NP. Now, what do I mean by that? A problem in NP over here, it is also exponential, and a problem in NP hard over here, it is also exponential. Now you can say that okay, if this problem is exponential, then why it is not in NP? This should merge over here, but that is not the definition. I cannot say, that's what I discussed in the first place. I cannot say a problem which is taking exponential time is an NP problem. I cannot make that statement. That's an observation. Getting the point? So that's why this part is mainly discussing about statements. You have to be very clear about it, otherwise we get confused. See, the concept is not difficult. You understand the concept, you would be able to answer all the statements.
So basis this diagram, it looks like certain NP hard problems which have been solved, and compared to NP problems, those are NP complete problems.
Exactly, exactly.
And I mean, there could be some NP hard problems which have not been solved, even though problem statement is known, but which has not been solved.
Yeah.
That is beyond NP and NP complete.
Solved means not solved. I would say here it means that, so to say that, uh, not, so there is nothing about solve. Solve is all of them are solved, but the idea is they are taking exponential time. So when I say NP hard problems, that means they are taking exponential time, but this part, only this part, the non-intersecting part. That means these questions are those questions whose solution takes exponential time, just like NP problems, but I cannot verify them in polynomial time. Definition of NP was you can verify in polynomial time, right? But if I am not intersecting these parts with NP, that means these problems are not verifiable in polynomial time. There are problems like that, verifiable in polynomial time. NP was at least verifiable in polynomial time, although it took exponential time to solve. But NP hard problems, as we have discussed, it is much harder problems, which is much harder than all other problems in NP. So that means these problems are not solvable, so obviously, but it is even not verifiable in polynomial time. The verification of this algorithm, that is the checking algorithm for this problem, also takes exponential time. So these are so hard problems. So that's why we call it NP hard problems. And what is the motive of coming up with NP hard problems? The motive is this real life example that we discussed, that you have to only compare with only one NP hard problem, your problem, and you can say your problem is a very difficult problem to solve. Fine. So that's the idea.
But why there should be an intersection between NP and NPHP?
Correct. Why there is an intersection between? Which factor is not? Sorry, not. Which factor is actually keeping this part separate from NP? That factor is not verifiable in polynomial time. Correct. Let's say I have some parts of it which are verifiable in polynomial time, and along with that, they are as hard as any other problem. That's what I have written over here. Any problem which is harder than all other problem in NP, which is the property of NP hard, right? This is NP hard. This definition is borrowed from NP hard. But along with that, that problem is itself a member of NP, which means along with that, that problem has verification algorithm which is polynomial. So that is NP hard, NP complete. Okay, so NP, this whole circle of NP hard. So I can always say NP complete. This is a statement. Now this is not an observation. NP complete is a subset of NP hard. This is a statement. By definition, this is coming. Okay, because if you see this, then you would understand why that is a statement. NP complete is nothing but NP hard along with NP. Okay, but so see, that's what I'm saying. Do not assume that I have drawn this non-intersecting part like this does mean that NP hard problems are not exponential, because your assumption that NP problems are exponential is wrong. NP problems are observed to be exponential, so I cannot force NP hard to be a part of NP. I can have NP taking exponential time, NP hard also taking exponential time, and I can keep them separate and say that you have not given in your definition that if I take exponential time, I must be NP. Is that a condition you have told? No. I can take exponential time and I may not be in NP, because NP's definition does not tell the fact that exponential algorithms are NP problems, right? So that's why I am keeping this separate. This is not intersecting. But some problem which are as hard as any other problem in NP may have verifiable algorithms of polynomial time, and those problems are the intersecting part, and that is my NP complete. Okay, a bit, I mean, it's better to, simple thing, but you have to listen to it one or two more times and then maybe think about it. It's not very difficult. This is the only thing that is required for understanding. If you go into the details of these things, it would be a bit more out of the scope, but yeah, that's the idea. If you go by the definition, this diagram should be very clear. NP problems are problems which are verifiable in polynomial time. I am not telling you that all problems which take exponential time, they are NP. If I'm not telling you, I can have exponential time and I may not be in NP at the same time. That is what NP hard means, which is this non-intersecting part. Okay, and NP hard's properties, I must be as harder as any other problem in NP. That is fine. That is not a problem. Now, among all such problems which are as hard as any other problem in NP, there can be some problem which are itself lying in NP. When I say itself lying in NP means what? There can be some problem which are as hard as NP's all other problem. Along with that, those problems are also solvable. Sorry, all those problems are also verifiable or checkable in polynomial time. Those problems we call NP-complete. Okay, so this statement, please rehear it once. I think it should be clear after. Okay, there's nothing very conceptual about it. This is the definition and discussing the definition, the corollaries of that. Okay, so this part is done. Now reduction. So when we were saying these comparisons, when we were saying that one problem is harder than all other problems, how were we doing that? Now I tell you that one problem is harder than any other problem by definition, but how actually that is done? So that tool of comparing two problems, we use the term comparing, right, to check which one is harder. That tool which compares two problems is what we call reduction. Okay, that tool is reduction. Reduction means what? You are converting. Now comparing to converting. This is more related to converting than comparing. Reduction means converting. Okay, but the essence is of comparison. But you are doing it by converting. What I mean is, it would be clear once we discuss the example. Converting a problem into another problem. Now, why would you do so? The thing is, when you are converting a particular problem into another problem, what do we mean by that? The first, by the meaning of conversion over here means all input of, let's say, the first problem, a problem is A to another problem is, let's say, problem B. All inputs of A is transformable okay. All inputs of problem A is transformable. That is, suppose I convert, so let's say your problem A dealt with like this, some representation, right? This is the input of your problem A, and let's say problem B deals with a representation where you give two integers. Okay, so you may give problem B like this, that the number of ones is equal to 4, number of zeros. The input of problem B might be something like this. Okay, the input of problem 1 is this one. The input of problem B is this one. So these two problems inputs are different because these two problems are different. But I have mapped the input of problem A, the logic of into the logic of problem B. Getting the point? This mapping is what I am calling transform. So this is also discussed by sir in the slide, that the input of one problem is convertible into the input of other problem. After you do the transformation or conversion, you apply the input into problem B. You solve the problem B, get the output of problem B, and then when you get the output of problem B, you again do the reverse comparison. That is, sorry, reverse conversion. What you do is that output of problem B, you map it into what could be the relatable output of problem A, if this is the output of problem B. So let's say what I mean is problem B actually deletes all the zero, right? And the problem is simply, let's say, takes a binary string and prints a binary string. So problem B would say there is 1 0 is there, so it deletes that 0 and it would return number of 0 is 0 and number of 1 is 4. Okay, the corresponding output, this is the output of problem B. The corresponding mappable output to problem A would be 1 1 1. Fine. So you did not know how to solve problem A. Of the inputs of problem A to convert them logically and semantically in a proper manner into the input of problem B, solve problem B, right? And then the output also you did a reverse mapping to problem A. So that's a kind of shortcut trick, because only reason is you did not know how to solve problem A efficiently. So this is the whole idea of reduction. When you don't know how to compare or solve any one problem, but you know another problem, then you have to actually check whether that another problem is related or comparable or transformable to the problem which you are not able to solve, or which you want to compare. Once you can do that, then you can simply do this step. Map the inputs, get the output, relate the output in a reverse manner. Okay, so this process is reduction. Fine. Now, one fact about reduction. That fact is, suppose I have a problem. Let's not take AB because you may get confused from this example. But the idea of reduction is this one. Now, the fact about reduction is, so let's say I have another problem gamma. Okay, and from this gamma problem, I have applied some transformation to convert this problem gamma into, or let's say not transformation, let's use the exact term now. That since we have now learnt about reduction, what I say is from gamma we do reduction of gamma into, let's say, phi. So gamma is a problem, phi is another problem. We have reduced the gamma problem into phi problem. Fine. Now the fact is, when I am doing a reduction, I am applying some other techniques, right? I am doing some work, not techniques. What I mean is I am doing some work to apply the logic correctly. I cannot just arbitrarily do any transformation. I have to keep the semantics, logical while doing the transformation. Correct. So I am doing some hard work in order to convert the problem gamma, in order to transform the problem gamma into problem phi. So that means I can say that problem phi is harder than problem gamma, because I have done some work on gamma to get to phi, right? So phi as a problem itself must be harder than gamma, because it needed some work to be done on gamma to get to phi in this transformation, right? Transformation. So from this diagram, I can make a statement, and there is a fact or statement. If phi is not solvable in p time, polynomial time, okay, then for sure sorry, if not gamma, if gamma if gamma is not solvable in polynomial time, then for sure phi is not solvable in p time, because we discussed that phi is harder, right? Now if gamma itself is not polynomial time solvable, then I'm doing some extra work to make it more difficult and get to phi, and phi is more difficult, and that's why if gamma is not solvable in polynomial time, phi must not also be solvable in polynomial time. So this is a statement, and please understand this statement is very important for this topic, that when you reduce a problem into another problem, the problem to which you reduced, right, that problem is harder than the problem with which you started. Okay, now accordingly, if the problem where you reach, that is phi in this case, If that is a harder problem and I tell you a fact that phi is solvable in polynomial time, let's say I tell you the fact that phi is solvable in polynomial time, you know that phi is more harder than gamma, and I tell you that phi is solvable in polynomial time, that means the harder problem is solvable in polynomial time. That means the easier problem must obviously be solvable in polynomial time. So, given the fact phi is solvable in polynomial time, gamma is definitely solvable in polynomial time. Other way to state is, given the fact gamma is not solvable in polynomial time, phi is also not solvable in polynomial time. Okay, so you do not have to remember this. Only idea that you need to keep in mind is this is harder, and then the logic would apply automatically. So if the harder problem is not solvable in polynomial time, it is solvable in polynomial time, then easier problem is definitely solvable in polynomial time. If easier problem is not solvable in polynomial time, then harder problem, obviously it is much more harder, so it would also not be solvable in polynomial. This is very important. Please keep this thing in mind, and this from the exam point of view also, and from your understanding point of view also.
Many true false could be
Yeah.
questions could be done from here.
Yeah. But once you understand this idea, the only thing you have to keep in mind is the reduced one is harder. That's it. Bottom line. After that, when you see the statement, accordingly judge by keeping this thing in mind. Okay. There can be multiple permutation and combination of the statement, but only important concept is the reduced version is harder, and that's logical also. I mean, you have a problem, you are making some work on that, and then you get to another problem. Obviously, the second one is you are adding some work, so it has become some bit more difficult. Okay, so yeah, that is reduction, and we actually discussed this transformation. Sir has taken one or two examples for, let's say, the network flow problem. We have done that using matching, bipartite matching. So that is one example of converting one problem into another, transforming one problem into another. Also, the three set problems are as discussed. I'm not taking those particular examples. What I wanted to discuss was the overall idea. This is the fundamental idea. Then you can take those multiple examples are there. All problems are converted into another problem, and all those things are going on. Fine. But this transformation and this idea is the overall basic skeleton of the concept. And one important thing also, that this transformation which we have written, right? We have done it in a random, arbitrary kind of manner, but there are multiple, as you can understand, obviously, there are various constraints, multiple rules and principles that has to be followed while doing this conversion or transformation. Those things are not there in our discussion, but it's important to understand those rules exist. We cannot do some arbitrary conversion, because if you do some arbitrary conversion, the semantics would be lost, right? The semantics of the problem, the logic of the problem would be lost. So there are many rules which you should follow. By following those rules, if you can transform the input of one problem into another problem's input, and you know the way to solve this second problem, then you can get the answer for the first problem. And this is a very valid, I mean, cutting edge area of research in theoretical computer science now. I mean, since back also, but now also it's going on. Okay, so that was it regarding NPP, NP-complete, reduction, and all those things. Any doubt in this, you may ask. Otherwise, we will just discuss the KMK algorithm now. I mean, the live coding. Fine. Okay, just go through the lectures, and I would request all of you to please go through this session, mainly the statements. Just hear the statements, what I tried to discuss. Those statements are very important, because that's what I said, right? When you this is a very classic example of the error that we generally do. That I mean, this thing, right? That NP hard. NP hard is exponential, NP is also exponential. But I am not bound to put NP hard in NP. The reason for that is the property of NP is not restricting me to have a exponential time. I mean, even if I have an exponential time, I am not bound to get into NP class. Okay, because NP's property is not saying that it must be exponential. NP's property is saying it must be polynomial time verifiable. Our observation is NP is all of the NP problems are exponential problems, but that is our observation. That is not a fact. Okay, so that's why NP hard and NP are separate. NP does not mean problems are solvable, not solvable in polynomial time. NP class does not mean problems are not solvable in polynomial time. I cannot make that statement. Okay, this thing is very important. It comes in mostly all of the exam. Okay, NP problem means these problems are not solvable in polynomial time. Wrong statement. It's not proved. It's an observation. Fine. NP is a subset of sorry, P is a subset of NP. This is also not a fact, because once I say P is a subset of NP, that is an observation yet to till date. Because, or you can say it may be a subset or it may be equal to. That you can say. If you have some notation of saying maybe in mathematics, then you can say that. But otherwise, if you directly write NP, P is a subset of NP, that is yet not proved yet. Because once you write P is a subset of NP, that means P can never be equal to NP. And if P is not never equal to NP, if you are making that statement, then you are trying basically claiming to solve the ambiguity of whether NP is equal to P. Right? So you have to give the proof for. So all these are observation. Statements are NP complete is a subset of NP hard. That is a statement, right? And NP problems are polynomial time verifiable. That is also a statement. Okay, fine. That was the summary. Okay, now I would share a Replit link. Only one or two problems, let's say, we can discuss. Easy problems, not take much time.
One thing, how to find the minimum cut, how to decide where to do the minimum cut in that algorithm.
That you have to take the flow now. If that wherever the minimum cut is there, that should be the bottleneck for the maximum flow that you are getting. So you take all the possible sets of vertices, keeping the source and terminal, sorry, source and destination separate in two sets, and then add the vertices and check where you are getting the maximum flow. Isn't that discussed? I don't know.
No, see how I am approaching is that from the target,
Yeah.
wherever just before the target, whichever there could be in a particular path, there could be multiple zeros. So just the adjacent zero from the target, we need to start cutting, making a cut line from there.
No, it may not always be the case. Okay, after that, what will you do? Adjust it then?
Yeah, then that will be a cut line, and then basis that minimum cut line, adding the weights and finding the maximum flow.
So in the residual graph, you're saying once the whole graph is ready, then you are making the zero cut line over there?
Yes, 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 yes.
Okay.
After reducing everything to zero.
Yeah. That should work.
How it was discussed in the previous live session, like Atul sir had suggested to make a list of possible paths and then
That is
listing the
how
minimum.
actually it is done, and the reason for that is, see, there are multiple corner cases. I would try to think of one where the process you said that seems okay, but I think there may be corner cases where it may not work. I'm not sure about it. We'll try to think. The idea is there may be some cases where it may not work. Okay, so the basic idea is you take all possible paths, or basically all possible. That's what I'm saying. Only fact is you would in the minimal cut, one set would have the T and another set would have the source. You do that and then simply add vertices. That is basically checking the possible paths. Take paths, or in other words, add vertices and check what is the flow coming out of these two sets of vertices. Wherever you get the set equal to the max flow, that is your min cut. I mean that those two sets are your
So
min cut.
basically, this is also hit and trial case. I mean, there's no concrete rule for that.
Uh,
I
if
mean,
you
to trying a boundary for a minimum cut.
if you
I mean,
get the max flow,
finding the maximum flow after
yeah,
reducing the graph is that part is okay.
yeah,
But then suppose it is asked which all edges will be there in the minimum cut.
correct. That's not trial and error that way. It's kind of trial and error, but not that kind of trial and error, because all you have to do is make multiple sets, two sets, not multiple pair of sets in each. I mean, so two group, right? One, you make two sets, In one set you put S, one set you put T, and then let's say add one vertex in the first set, another vertex in the second set. And then you say what is the flow coming out between these two sets, right? You check that. If that is equal to max flow, this is your min cut. If that is not equal to max flow, add other combination of vertices. So you have to check that multiple combinations of vertices into two sets. That part is a trial and error. That part is trial and error. But you are also having one condition, right? So that's why I cannot say it is always trial and error. You have the condition that the flow between these two sets should be equal to the max flow. So once you find the max flow, you can just make these sets and check when the flow between these two sets is equal to the max flow. Once it is equal, that is your min cut.
No, but when we make the residual graph,
Yeah.
then certain edges become zero. Not all the edges. Certain edges become zero.
Yeah.
Meaning that no, we cannot. Flow cannot happen through those edges in subsequent path. We
Correct.
cannot take further path through that. So zero means that there is no flow through that is possible after we are reducing. After reduced graph is done.
Correct.
There could be some edges or path through which flow can happen, but then ultimately in the final reduced graph, all the paths will be having a particular edge which is having zero.
Yeah.
That is what my observation is.
That is
That
correct.
in the
That is
final
correct.
reduced graph,
Yeah.
all the possible paths will be having a zero edge, so that no further reduction can be done. So this is basically that zero path is leading to
Minimal cut, right?
no flow, possible flow through no final reduced graph.
Yeah.
Final reduced graph of the no more further reduction is possible, because each possible path will be having a zero edge in that, so that we cannot take any further flow through that.
Correct. I am saying that that's correct. There is no doubt about it. But the only thing is, uh, you are saying that zero in the residual graph, it is zero. You cannot further reduce the flow, and that's why that means that is the maximum
Yeah,
possible flow
that
through that path.
zero
Okay.
in the residual graph, final residual graph means no flow can happen through that.
Correct. Yeah. So that's fine. And that means you cannot actually change, and that's why that path is basically leading you to the max flow, and accordingly you can get the min cut over there from that path. But the problem over there is, if you get a zero and you go through all the edges.
The way Atul sir explained, that was quite easy and kind of mechanical way to find out the maximum flow
Yeah.
in any particular graph, which was quite easy. But then this finding the minimum cut, which all edges will come, that was not clear.
Minimal cut, you generally the algorithm says that you have to go through the making the sets, but I have not seen how it is explained or how it is discussed. Uh, Maybe
Okay, I'll find out.
okay, but let's do one thing. Maybe in the mock session, na, we would discuss. I would try to discuss the min cut once. Okay, most probably I would not get any session before that. Uh,
In
uh,
chat.
in the next session, I can discuss. Fine.
In the chat, I have also requested something.
Okay, then I will check. Fine. No issues. I would try to discuss it over
No, in the chat. Could you please look at the chat?
this chat. Extra session to discuss quiz questions and PPAs. Okay. Uh, next week. Yeah, okay. Let me discuss it. There are some logistic issues, but yeah, I will. Okay, noted. Right.
Discussing quiz one and quiz two questions, I believe, it will clear lots of doubts for final
Fine.
quiz.
Fine. Yeah, before NTAM anyway, let's say we would do that. But in the next week, I'm not sure about. After that, okay. Anyways, kept in mind, noted. I will do check with the team. Sure. It's already in 40. Let me just. Yeah, so I have shared a reference link. If, please read the question and try to think about the way you would approach it. If possible, try to code a few lines. After some time, we would, after let's say 5 minutes, I would discuss the problem. Just a second. I've yet not published it. Just a second, I would publish it. Yeah, I published the problems.
Two problems are published.
Yeah, two only I published. Okay, so let's briefly discuss this. I mean, basically a simple problem that you have this kind of that automaton that we discussed, basically a transition between different states on different inputs. That's the idea. So you have to parse one input, and then you have to simply move from one state to another depending upon what is the next character in the given input, right? And depending upon the given states, configuration of the states. So how will you get the configuration of the states? The configuration of the states is given in your this T transition dictionary, right over here. If you see over here, this dictionary is giving the transition where the each key of the dictionary is basically the initial state q naught as q0 on accepting the character b goes to the state q0. Accordingly, the next key is state, initial state and the input, and the final, this value is the final state. So on Q0, if the system is on Q0 currently and it receives C as the next character in the string, then it would move to Q0 again. Accordingly, you have this all the configuration mentioned. So you have the question is giving you a starting state and the configuration and the destination, right? So all you have to do is simply start from this Q0 or the starting state, go through the transitions by accepting the characters one by one from the string, okay? And then finally, when the string gets exhausted, the last state which you are in, check what is that state. If that state is equal to Q2, that is the given final state, then you return true, else you return false. Fine. So that's what we have to do. I mean, to take some time to think about the code and do the code, but concept is very simple. Not also very difficult in coding. Just you have to think about it a little bit. That's it. So I have the is accepted function. It's already mentioned. You have to write the is accepted function, which would consider the T as the transition functions given on the configuration. Start and final are the two states, start and final state, and S is the string by accept. I mean, from which you will pick. We will pick the consecutive characters. Fine. So let's do that. So let's say I have to start from the starting state, right? The one which is given to me. So I would say that current state equal to start. Okay. After that, what I would do, I would, once I got the start state, I would run through the first configuration which is having the start state in the T, right? I mean, I am currently at the starting state. So and the first character of S which I get, start state, comma, that character equal to whichever state is there, to that state I would go, right? So what I would rather do is, in order to repeat this process, I would say that I have to exhaust the whole string, correct? So at first I would write the code for that. Let's say for any the current symbol, right? Let's say the current symbol, or let's say current character in the string, right? So the current first character which I have, the first iteration. Now if there is a configuration to reach the state starting from the current state, so current state comma the current character, right? Current state comma current character, right? So this is the format in which our the configuration, the T is given, right? The T dictionary. So if there is such a configuration or there is such a transition, right? Then what will we do? We will go through that transition's value and then store it in the next current state, correct? If this is the case, what we would do? We would write current state equal to the transition value, right? So T, the value is given by this one. Just taking that, so from whichever current state and current character to whichever state I go, that state I am storing as the new current state. And from that again I would repeat the same process. Oh, sorry. Right. So I would do this, or else if there is no such transition, that means I have come to a state which is, I mean, dead state. I cannot proceed further, right? So in that case, I will return false. Okay. So else I return false. And one more thing. So if the, I mean, I have to check whether at the end of this loop, right? At the end of this for loop, right? If I have reached the final, I mean, string, right? Sorry, not string, final state, right? The state that I have currently reached is equal to the final state. If that is the scenario, then I would return true, correct? So that was it. Okay, so then I have to just rephrase it a little bit. Okay, so let's say not in T. Return false. Yeah, fine. So this is done. Now I would just check whether the final state that is given to me is equal to the state where I have currently reached, right? The last state, which is my now current state, is equal to final state or not, right? If it is equal, you return true now. If it is not equal, then you again return false. Fine. So simply traversing through the configuration and then simply checking which are the states that we reach. And finally, once the loop ends for the string S, we are checking the state that we have currently reached, right? The current state at the end of the string, is that equal to the given final state or not? If it is so, you return true, else you return false. So let's check. Fine. So just a simple traversing code. Now let's go for the second example. Sorry, second question. So this is the second question, right? So this question actually says you, so a string is called a happy prefix if it is a non-empty prefix which is also a suffix. So a string is such that you have been given a string and the prefix of that, some prefix of that string is also the suffix of that string, right? if there exists any pattern like that in the string, you have to find the longest such pattern. That is the longest set of characters in a string, which is its prefix as well as its suffix. Right? We have to print what is the what are those characters which is the longest and both prefix and suffix together. So, so I've released this question, but still let's wait for 2-3 minutes and then we will discuss. As you can see that, I mean, it's just directly about KMP algorithm, because KMP actually works on the basis of this idea that you check for a prefix, check for a substring which is working as both prefix and suffix together. If you do not get any such substring, then you actually reduce the size of the prefix, and then again you check whether with this reduced prefix is there a match or not. If there is a match, then you proceed. Otherwise, you again reduce the size of the prefix. Again, if there is a match, you proceed. Otherwise, you just go on like this until the prefix becomes 0. If the prefix becomes 0, then you simply proceed further with the other part of the string. Right? So that's how KMP works, and this is what exactly asking you in a different way. It's just KMP. Okay, so try to do this code. I'm not, since this is directly KMP, we are not going into the details of this application. Just write this code, practice this, and we have noted the things. We would most probably try to schedule one extra session about this quiz and all in the next week. Let us see if we can do it. Fine. Okay, fine. Thanks all of you for attending the session. Thank you.
Thank you, sir.